Yeah, if any of you don't know me, I'm Talay. I'm a idea PhD student in the lab. And with Ferenc, I'm going to be presenting differential privacy in the reading group today. As usual with these reading groups, we're not the experts. So there may be people around who know more than us about this or adjacent topic. And if you're one of those people, then it would be great to have your contributions. I think we have questions and discussions. That's the point of these things. Okay. So an overview of what it's going to be. Differential privacy is applicable to all sorts of topics where you have to process data, not just machine learning. So in the first part, I'm going to talk about differential privacy in general, starting from the basic motivations and the differences, the different notions of privacy, and going through some of the technical definitions. And then Ferenc will talk about differential privacy in the context of machine learning in particular. One thing that arises with differential privacy is that you have this kind of tension between the idea that you want to preserve your own privacy, which means holding your information to yourself, and the user of the data wants to learn things, which means they want to gain information about the population. So kind of navigating this tension is one of the main themes of differential privacy. Okay, so first of all, motivation, why bother? I think everyone probably agrees that privacy is important, or at least that other people care about privacy. So I probably don't need to say this, but I'm going to say it. So from an engineering perspective, people who work in machine learning or do research in machine learning, probably it's important that we understand how differential privacy works, because we may have to interact with it. But also there's a wider societal point that's like, people in general are concerned about privacy. When you talk to people about your work, probably some of it, well, not experts, actually. When you talk to non-experts about your work, probably some of the things that they like to talk about are things concerns around safety or fairness or privacy. Right? So some of these around privacy is a bit difficult. So it's kind of important that if you want to engage with people in the wider society about privacy, you also need to have a good understanding. Now, like you can think about privacy in various different ways, and differential privacy is one formalization of privacy. So, kind of understand how we get to that formalization, it's a good idea to think about these more naive approaches that you can easily find ways in which they don't work. So I'm just going to go through these one by one. Firstly, anonymization. The simplest form of anonymization is you remove the unique identifier, like a name, from the data, but then just let people do whatever they want with the data. And it's kind of easy to see this doesn't work. If you think about students in CDL, you may not have the name, but if you know something like the year group and the nationality, you probably have to narrow it down to like one or two people. And of course, in many scenarios, people who might be using the data product also have a lot of information from other databases and so on. So it may be surprisingly easy for them to identify people from information that you might not think is unique to them. Second, this idea of large queries, you might think, well, yeah, I mean, you're allowing people to ask very specific questions. If you just have, summary statistics, means over large groups, things like this, then that may be a bit safer intuitively, but you can construct small groups and big groups by big minus. Like if you ask about a group that's a lot of people plus me, and then another group that's just a lot of people without me, then the difference between those calculations will be minor things. And the third idea, benign facts may not be benign. There's an example in the differential privacy book, which I'm going to kind of take here. In some contexts, you might think that healthcare data is sensitive. Often people are concerned about this. And one example might be that I, for example, use Tesco Club Card, right? Because I want the discounts. And they then track all of my purchasing habits over time. And also I have a family history of type 2 diabetes. So you can imagine that it's realistically plausible that at some point I could become pre-diabetic. And Tesco, tracking my purchasing history over time, may realize that I can become pre-diabetic from a sudden change in my purchasing habits. Things which have less sugars and so on. So you might think that what food I buy is not really exposing any particularly important information, but in certain contexts it may. With all of these things, you can think that the problem here is the kind of questions you're allowing people to ask, like the differencing, for example. Clearly, that sequence of 2 queries is exposing a lot of information about an individual. So you might want to audit those queries to make sure that people don't ask questions of data that will give them too much information. But if we're just asking simple questions of a database, this might be easy. Think about all of the possible queries people could ask, or the whole complicated process of a learning algorithm. It's like not really feasible to audit everything that someone can do with the data set. And of course, if you refuse to do something, that's also kind of leaking a bit of information in where someone may be able to leverage it. So the problem with all of these things is that not only do they not work in some circumstances, but they don't really have any like formal basis. Like it's not clear exactly what the objective is and how far they're going towards achieving it. And another thing to mention before we proceed is that there are a lot of other ideas in this space that solve at least related problems. And some of them are like using methods from security, like cryptography, and things like secure multi-party computation, and doing things like federated learning, when you minimize the amount of your own data that you transmit to the person doing the learning algorithm. And these solve different problems, really, but they're kind of complementary to differential privacy. And once we have the definitions of differential privacy, we can maybe reflect and think a bit about some of the differences. Inevitably, when you get into any formal definitions, you need to build up a lot of formalisms. So bear with me. The scenario in differential privacy is that we're kind of thinking about 2 databases, X and X prime, which differ in one point. Like one point in the data set is different. Like there's one fewer in one of them. The canonical example is that you think about X containing the data, including your contribution, and you think about X prime being without your contribution. Right? So that the difference between these is your decision to participate. And all of this data, the database or data set, is in the hands of a trusted curator. And any user, like someone who wants to perform a learning algorithm or ask queries of the data, we kind of model that as them sending a function f that they want to be calculated on the data set. And then the trusted curator instead uses a modified noisy version of the function phi, which is somehow private in some sense. And so there are some examples here that we have that database kind of referring to earlier about students in CDL. Some really simple examples of queries could be, I want to know the number of students or the average age of the students. So I'm thinking about why my data is going to be available on this data set, is my privacy going to be exposed? Okay, and the philosophical principle of differential privacy, as I see it, is that your choice to participate in the database shouldn't bring any disadvantage or shouldn't leak any individual information about you. And there's an important distinction here between like your individual participation bringing you disadvantage and the database as a whole bringing you disadvantage. So going back to that diabetes example from earlier, if I'm participating in some medical database that people determine from that I become pre-diabetic and therefore I face some adverse consequences, that would really be a leak of my individual privacy. But of course, if I participate in a data set from which they learn that South Asian people have higher predisposition to type 2 diabetes, that would also increase their perception of my risk of diabetes. But it wouldn't be because of my individual participation, it would be because of the population-wide participation. Like, everyone would need to opt out, but they're not to learn it. Does that make sense? I see some yeah. Okay, so in order to define this, we define this privacy loss, which is like the log likelihood ratio of what the user learns from the computation noisy function. So I'm going to use this kind of notation throughout, that if the one data sets X and the other is X prime, then the distribution of output is P for phi computed on X and P prime for phi computed on X prime. Right? And so then the privacy loss is log P over P prime. And yeah, and this is a random variable, and this also is randomness. It's the randomness in that function phi. So you can think that depending on the randomness, you may get a response that's more or less informative. And this aligns with the kind of philosophical motivation I gave before, in the sense that if you think about someone who's looking at these responses with a lot of information, and they want to determine something like whether you were in the database knowing everything about you and the data set, someone who wants to find one feature about you, then their like Bayesian computation is to look at that log posterior probability ratio. And this log likelihood ratio is that increase in that log odds in favor of you being in the database, or you having a particular feature. These things like, it's the number of NAS, or if we did log based, the number of bits of information that they gain in answering this question. And there's kind of a worst case assessment in the sense that for them to really understand how the randomness in the function phi affects the distribution of the output, they kind of need to know a lot of stuff in general, right? Like how my age would affect the average age of students. You need to know like how many students there are and what the other ages are, what my age is. Like, it's not going to be like that straightforward to work it out unless you know all sorts of things. But in the worst case, an administrator might know a lot of this.
So
yeah.
So lambda x to x prime. So is that an expectation over p?
No, this is just the log probability ratio. So if you think about it from a sampling perspective, it's like you compute phi of x, right, which is random, because phi is random, and then you compute the probability of that output under p and under p prime and that log ratio.
So that lambda is a random variable.
Yeah.
Okay. Cool.
Okay, so then that brings us to the definition of strict differential privacy, which is that you'll say the random function, like this function phi, is differentially private with parameter epsilon if for any pair of data sets that differ by only one value, this privacy loss random variable is always going to be less than epsilon with probability 1. Or another way of saying this, that the worst case privacy loss is something less than or equal to.
That's a difficult question about the setup. Might be a silly question, but is the user allowed to query the same function twice, and does the curator know that it's like, imagine that this was a function, adding back and random noise, right? But if I'm allowed to send the same query 1,000 times, then I have a pretty good estimate of the mean, and the calculation does that. So is this noise, I'm assuming that it's this, I'm just wondering, is this going to be, are there going to be limitations on my allowed queries? Is this going to be structured in a way that's actually deterministic, and so I will get the same result every time?
So this is a good question. So at the moment, we're just thinking about the scenario in which any user can ask any one query.
Yeah.
Right. And as you say, if someone's allowed to ask multiple queries, then they can learn a lot more. So we're going to need to calibrate the randomness scarcity function in account of how many queries we expect us to ask. And that's going to be quite an important concern. And of course, if we know the kind of questions they're allowed to ask, kind of queries they're allowed to ask, then you may be able to also take advantage of that. For example, by giving the same noise if they ask the same query. Okay. So now that we have the definition, we can reflect on some of those things from earlier. So compared to the method in cryptography, what you're usually thinking about there is that, like, I want to communicate with someone, then I use like some shared secret information to communicate privately with them in a way that an adversary can't reach. But in the differential privacy setting, we don't really have this distinction between the desired end user and the adversary. It's like everyone is treated the same. So you can't really directly just lift methods from cryptography and use them to achieve this kind of privacy, this notion of privacy. Information theory is maybe another thing to contrast this with, because we've interpreted the privacy loss as being the amount of information about this particular comparison that you leak by participating. But in information theoretic approaches, we're usually thinking about doing averages over something. Information theory is a theory of taking averages. So if I am reassured that my privacy is not leaked on average over databases or on average over the randomness of the noisy function. These are not really that useful guarantees. So that's kind of like saying that, or in some case, there could be a scenario in which accuracy is dramatically leaked. But don't worry, the average person will be okay, and that's going to help you. And I've kind of already mentioned about the thing that there's previously the guarantee for these small changes in the data set, so protection of individuals rather than of groups. Because in the end, you want to learn things about groups, like population level things, like with the diabetes example. Okay, so that's the definition, which hopefully made sense. And now, how do you achieve it? We're going to look at that. So the idea is you just add noise.
Sorry, I
Yeah.
just wanted to ask a question. Maybe it's like a bit naive, but in order to get a better understanding for what, like the definition, like why this definition is useful, if this definition, if for example I have a system, like I have a setup for which your definition, the definition that you gave does not hold, as in this system does not satisfy the probability that even this criterion is less than 1. What would happen? How could an adversary tell something like about, extract information about individuals in the data?
Right. So probably the simplest example is to think about the examples from the beginning, where you have like, okay, I mean, like a really simple example is that the function is to evaluate the age of anyone who satisfies certain criteria. And you can pick those criteria to be that narrowed down to like one person. If you kind of know enough about the data set to know that there's only one person who satisfies the criteria. That makes sense?
Right. So you have to like have some knowledge about X or X prime, right? It can't just be, just starting making like queries without having any knowledge.
Yeah, usually that would be the case, right? And usually you would also expect people to have some information about, if you think about an example like sentiment data, people have a lot of knowledge about people in general from other data sets, for example. So they usually have a lot of site information, and that's why we have this. Okay. Yeah.
Can I also think what sort of epsilons are normally used here? Like what kind of epsilons make sense? Like is this setup dependent or?
Good question. We'll come back to that.
Okay.
You want epsilon to be small, right?
Sure.
But how small?
No, but these are log ratios. So.
Yeah. But if you think about it as the number of, if we had it in bits rather than that, number of bits of information you did, and it's like, how many bits of your information are you willing to use? I guess that's kind of roughly the location you want. Okay, so a simple solution is just add noise, and then the function output is random. So and these are sufficiently to use. The noise is not too severe, then they'll still learn what they want to learn. But there might be some issues with that. So this first one, what are underestimates and much less an overestimate? So if you just add Gaussian noise, say, then that might be a problem if, as the end user who wants to analyze the data, you're much more worried about getting it wrong one way than the other. So as an example, if you looked at something like average calories, something to do with calories, with the purpose of cost of living is rising and I want to help people who are on low salaries, and you add some noise. When you corrupt the if your estimate of the average salary is lower, then you end up maybe having to spend a lot more money to give them social protections. The estimate of the salary is an overestimate, then you may not spend money on help people really need it and cause a lot of harms to them. And your subjective value of how bad these two things are may be quite different. So that's maybe something that needs thinking about. But we'll come back to that one because it's a bit complicated. Another thing is about the sense of scale of the function. So if I evaluate a function that these two adjacent data sets, like for example, the number of PhD students in the lab, if I evaluate that on data sets that differ by one student, the number of students is only going to differ by one, right? If I have noise of standard deviation 1 on a data set where the values of the function different by like 1,000, then clearly I'm just as easily able to distinguish them as when I didn't add this. Clearly the noise has to be calibrated to the scale of the function. Or you could say the sensitivity of the function to the data set. And we can formalize that definition in this way. So the LP sensitivity of f is the largest value of the p norm of the difference on adjacent data sets. You need to have some definition of what kind of data sets we're considering. And we'll use P1 and P2. So the one norm is just the largest absolute difference. Two norm is just the largest RMS difference. One way of getting strict differential privacy is by adding Laplacian noise. This works. You just need to add Laplacian noise that is scaled up according to the sensitivity of the function, and in inverse proportion to how much privacy you want. Right. You can already see some of this, like privacy utility trade-off, because if you want to be very private, then noise can be very large.
I was wondering, this might be a silly question, but when people think about adding noise to the data rather than the query, because it seems like that would, in a sense, overcome some of these issues of stride. Like, say you just, when I enter your information into the database, I add noise to your age, and then that noise is like scaled to age, and because now your information doesn't exist in non-chrome form in the database, like an adversarial user can't construct a set of queries to reconstruct this information because it didn't enter.
So you can add the noise to the data points instead. You just need to think about what's going to happen to the answer to the query. So for example, if I add independent noise to the value of each user's like age, for example, and then the query is the average age, of course the noise will become small, not on average. So you need to make those considerations. Okay, so this passing mechanism, why this works is really easy to prove. So I'm going to briefly step through the proof, just to like give an idea. So if you think about the R here is the phi of x, so the response that you get when evaluating the noisy function. And because you're just evaluating a deterministic function plus Laplacian noise, distribution of the response is just like a Laplacian noise around the response. And so the privacy loss random variable is the log ratio for f computed with x and x prime, which if you expand it out, then using the triangle inequality, you can get rid of the r, and that gives you the second line. And of course, the one norm of this difference between f(x) and f(x) prime has to be less than the sensitivity by definition of the sensitivity. So those terms cancel out, and that gives you the last term.
I think there's a question in the comment.
What is it?
When you add noise to data sets or most complicated, interesting data sets and applications, noise tends to dominate, and it is better to add noise to the query. That's good stuff.
Thanks. Right, so this is the Laplace mechanism, and it works. So that's good. So yeah, so maybe it's we kind of already talked about this, but it's good to just revise how the sensitivity works. Some of the considerations going for that. So for the number of PhD students CBR, I was saying before, if you add or remove a student from the data set, you're only going to change the number by one. That works. But the age is a little bit more complicated because if you add or remove one student, the average changes by, well, it depends on what the range of ages are and how many students there are. Obviously, if the number of students n is very large, then adding or removing one student is not going to change that average by very much. So roughly, you might say for n larger, it's going to be something like the maximum age divided by the number of students would be a couple of on how much it would change. And yeah, so if the noise is high, then our responses to queries are going to be less useful, less accurate. But on the other hand, we want to preserve privacy. So we have this tension, and these sensitivities are very much like a worst case change between data sets. So you can imagine that often we're going to end up with noise that might be a lot more than we need. If you think about, so maybe one way of thinking about this, if you compare the computing the mean to computing the median, they're kind of similar quantities, but the mean might be like worst case instance might be blown up by extreme ages, whereas the median is going to depend on these separations in ages, which will tend to be a bit more clustered. And we talked before about how your like you might care more about positive noise than negative noise, things like this, and here about how we're worried about how accurate some of the contacts, and kind of a way of dealing with both of these things is to assign a measure of how good or how bad a response is, like a utility function to measure that. And that leads to the exponential mechanism, which I'm going to go through only very briefly. So the idea here is that if you have a utility function for a given response input pair, then if you then create a noisy version of the function by outputting responses exponentially in proportion to the utility scaled by its sensitivity, then that's also strictly differential private. And one thing that's nice in the analysis of this is that because we explicitly consider the utility, you can kind of say that, oh, under certain conditions, the utility is not harmed too much in some sense if we do this. And also, the Laplace mechanism, the special case of exponential mechanism, when your measure of utility is just one norm distance. Right? So when positive and negative distance is the same, it's uniform. So this is kind of interesting if you want to look in more detail about these things. And it helps you deal with all sorts of like other cases where the measure of utility is going to be very, very different. Okay, so now we'll come back to the question that Chris was asking earlier about if you ask multiple queries, and that kind of throws up a lot of problems in different privacy, which can be well addressed by introducing an approximation. So if you apply many functions, ask many queries, let's say k of them, then the total privacy loss, the bound on it, increases linearly. You get k epsilon for k queries. And that's kind of problematic because if you say that, okay, I'm going to have this data set that I'm going to allow to be queried many times with arbitrary queries, then if I want the overall privacy loss to be fairly limited to some value I pick, like 1 now or whatever, then the individual queries have a very high standard epsilon because it has to be 1 over k. So that kind of feels like that'll end up being passively conservative. And one way to deal with this is this delta approximation to differential privacy, which is also called epsilon delta differential privacy. And the change here from what we had before is rather than saying that this privacy loss has to always be less than or equal to epsilon, we're saying that this has to almost always be less than or equal to epsilon, and with probability delta, at most delta, it can exceed that. There's like a bound on the tail. And I think the right intuition for this is a reasonable worst case privacy loss. Before we just had, we bound the worst case privacy loss. This is the reasonable worst case privacy loss is epsilon. And our definition of reasonable is encapsulated by delta, because we're saying there's some probability at most delta, which doesn't hold. So you, as a user looking at the system, you can say that, okay, this value of epsilon is sufficiently low that I don't care, like I may lose a bit of privacy, but not very much. And there's some probability higher, but okay, that's like 10 to the minus 5, and that seems okay to me. We want this delta to be much smaller than 1 over the number of people participating, so that you don't expect anyone's privacy to be exposed by more than epsilon on average. That makes sense. So I think understanding these definitions is kind of one of the most important things in like understanding differential privacy and use. And how this helps us with the problem of answering multiple queries is that by allowing this, rather than saying that when we ask multiple queries, they still have to be strictly epsilon differentially private, we say that we're going to ask multiple queries and allow a small probability that privacy is leaked by more than epsilon. And then that allows us to get this bound, which is a little bit hard to digest, right? There's a lot going on in that equation. But the important kind of thing to think about is imagine epsilon is very small, like much more than 1, then epsilon squared is small. So for k that's kind of like medium sized, then this thing grows like square root of k rather than linearly in k. And that's much slower, right? So you can kind of get away with being less conservative with your epsilon individual function evaluations, as long as you're willing to allow that extra leakage delta prime to be more than 0. And we could achieve strict differential privacy by adding that heavy tail Laplacian noise. And epsilon delta differential privacy is kind of convenient in a way because you get it by adding Gaussian noise, and everyone loves Gaussian noise. Unfortunately, the theory is a bit less tidy. So the noise you have to add doesn't look as nice. And I've given kind of 2 versions here, and that's way too much to digest. But basically, what it says is that the Gaussian noise you have to add scales up with the L2 sensitivity of the function, and inversely with epsilon, and then delta comes in there somehow via logic. So the smaller you want delta to be and the smaller you want epsilon to be, the bigger the noise and the deviation is going to be, which is what you would expect. And one thing that's of course convenient about Gaussian noise is that if you're doing Bayesian stuff, you probably know how to deal with Gaussians in your algorithms already. It always works out easily with Gaussians, unlike maybe with Gaussian noise. Okay, so I might briefly, I think there's enough time to briefly talk about this. There's this extension of differential privacy that's kind of not as crucial to understand, but I think it helps with some of the theoretical aspects, and people seem to refer to it a lot in more recent papers, so it might be a good idea to know a little bit about it. And this is zero concentrated differential privacy. The idea is that, as a rough intuition, when we talk about differential privacy initially, with strict differential privacy, we're saying the whole distribution of the privacy loss needs to be living somewhere up to epsilon. And then with the delta relaxation, we said that we can have some probability that privacy loss is more than epsilon, but it has to be small. And zero concentrated differential privacy instead talks about like how fast this distribution must decay, rather than just what's the probability in the tail. That's the like high level picture. Defined in terms of this radiant divergence, which if you haven't seen it before, it looks like that. And so I think it's kind of helpful to interpret everything back in terms of the privacy loss random variable, because that's something for which you might have a bit of intuition. And in terms of the privacy loss random variable, it's something proportional to the moment generating function. Right? It's a function of this alpha variable, which is the order. And the moment generating function is also not particularly helpfully interpretable, but hey, what can we do? So they look at alpha, they use alpha between 1 and infinity, and the helpful special cases at the extreme are when alpha is 1, it's the Kell divergence, which we all know and love. And it happens to be that in that case, this turns into the expected privacy loss. And when alpha goes to infinity, then this becomes the maximum privacy loss. Right? So those cases kind of make sense. And then you can imagine alpha in between because it's increasing, it's just some interpolation. And interpreting what we've previously done with strict differential privacy in terms of this divergence is that if you take when alpha is infinity, this max divergence, then strict differential privacy says that that has to be less than or equal to epsilon for every pair of data sets that is only by 1,000. Whereas zero concentrated differential privacy says that for every alpha, I want that that divergence to be bounded by some affine function in alpha, and the offset and the slope are the two parameters of this definition. Right. And if you want the when alpha is infinity to be bounded, then clearly you have to set rho to be 0. So in that case, it coincides differential privacy and epsilon differential privacy. And when you have a value of rho that's non-zero, it's like some sort of relaxation. And it's a characterization that guarantees that the privacy loss is sufficiently concentrated around 0. That's why it's called zero concentrated. And this ends up being useful because it can be, you can convert from this back to the epsilon delta definitions. You can imagine that the delta is like how much probability is in the tail, and this characterizes the rate of decay. So there'll be some link between the two. And people use this in analysis because you can analyze the Gaussian mechanism a bit more nicely than this. You don't get those kind of ugly expressions that we had before, and you can do other things in terms of group privacy and theory. So sometimes it seems like recently people have been setting their parameters in this kind of definition and then converting to epsilon delta to communicate that formulation. Okay, so that's kind of everything I had to say about the foundations of differential privacy, which was at least most of it made some sense. And now I'll hand over to Ferenc.
Anybody has any questions?
I've got one quick question. So you mentioned setting like the maximum value, like the maximum age or something, is like it's setting the sensitivity. But by kind of doing a few queries, I could probably work out the noise distribution. So is that leaking information about the maximum age by just even using it as a noise parameter?
Yeah, probably. So you would want to do something like place a bound on the age, like say that, well, I don't expect many of the students to be above 33, say. And so I'm going to, if anyone is older than 33, I'm going to exclude them from the computation and then add noise, which is like clipping the edges to make sure you have a reasonable bound.
Are there any assumptions? So, as I understand, the querying party does not have accessibility to P, which is the distribution of this P function computed on the data set that includes their data. They might know.
All of the randomness comes from phi, right?
Yeah.
How you add noise to the data set. So that they may know, right? Like they may know your protocol for adding noise. And the part that they don't know is they may not know like how F changes as the database changes. Right.
I thought P depended on the P is just distributed according to P. So,
So they probably don't have complete knowledge of P because that would require them to know everything already, more or less.
I'm just trying
But
to
they have a pretty good idea.
do they know? Like, are there any assumptions on like what the querying party knows about P prime versus P? Or is this not something that people worry about?
So you kind of assume that they may know P and P prime, although this is not really like exactly what they will know. So you allow that they may know these and therefore may be able to make decisions optimally by computing the log P of P prime, like the log observation.
One of the ways I like to think about that is you want to prepare against the worst case attacker. And that worst case attacker might just randomly know P and P hat. Like they might just have a random guess that coincides with the actual P and P hat. So if they happen to come with a classifier, however they obtained it, which is Bayes optimal with respect to P and P hat, that's the worst case attacker. So you should defend against them. And anybody else who doesn't, like that's the worst thing that can happen if somebody actually like knows all that information. But if you put a bound on that, then you basically put a bound on everybody else. Like anything that anyone can do, bringing their own data or whatever, sort of defending against all of those.
I think that some people like the idea of formulating different purposes with more constraints. So whether that's about what people know or how much computational power they have. But I read something good in the zero constraint DP paper where they say they introduce a third parameter and 3 parameters can be quite important. I think that's true. Like the more constraints you put on the formulation of the adversary, the more parameters there are in your definition. And it's kind of hard to pin down when it applies and how well it applies in each scenario. So one thing that's nice about this extremely worst case thing is that you only have 2 parameters, maybe even 1, and that's kind of easy to work with.
Thanks a lot for that presentation, I should also say. I wish I had a little bit more, spent a little bit more time with Talay. I kind of signed up to present about differential privacy, and then in the end I woke up at like 4:30 this morning to read the paper that I was supposed to present. So I think I can still say a few things about it because I've come across these topics before. But yeah, my level of preparedness I think is more in the informal regime compared to the formal regime. So this is a nice transition from the previous formal reading groups, as I understand they were, to the informal reading groups that are to come in the future. So what I'm gonna talk about is how this DP stuff works in practice, and particularly with machine learning. So there will be a couple of things. I'm going to show you examples of how, a particular example of how I've come across differential privacy in my work at Twitter. And then, but that's just a brief foray. And then I will talk about how to train machine learning models with differentially private mechanisms, how to ensure that the models themselves have this differentially private property and what it even means, and what sort of attacks it provides a defense against. And then finally, I will talk about DP and generalization. It turns out that differential privacy, usually you think about it as a trade-off between having a good model and achieving some other good goal, like being private. It turns out that if your model has differential privacy, that might actually be good from a machine learning viewpoint. It might allow you to, the differentially private models might generalize better. So this is the thing that I wanted to just show very briefly. It's recently published work by my colleagues and I. I don't know if you've seen this algorithmic amplification of politics on Twitter. What we did here is we looked through tweets from different politicians belonging to different political parties, and then we compared people who had algorithmically ranked timelines, so where the tweets that they consume are ranked by a recommender system, a machine learning algorithm, and those people whose Twitter feed is chronologically ordered. So they just see the latest tweet that anybody they follow tweeted. This is how Twitter used to work before 2016. And there's still a control group of about 1% of users who see their tweets chronologically ordered, and there's no machine learning going on in like ranking their tweets. So we can use this randomized control experiment roughly to measure the effect of the machine learning based ranking on what kind of political content people are exposed to. So we can look at whether the ranking shows more right-wing content or more left-wing content and stuff like that. I'm not going to talk about the conclusions of this study, but this was a big exercise in algorithmic transparency. Like this uses a ton of private data, what tweets people saw on their Twitter timeline. So it's based on like a bunch of private data that's not available through the Twitter API, like when you logged into your Twitter account, what tweets you scroll through, whether you post to look at a particular tweet, those kinds of things are completely private. But we are asking the big question that we want to make public, which is, do the recommender systems expose more people to right-wing content, for example? And so there is this tension between wanting to share some data publicly, but we obviously don't want to share the entire data set publicly because there's a lot of private data in there. So what can we do about this? And what we did here, which we were of course criticized for both by reviewers and I mean, rightfully, is that we just ran the big query on our servers and basically published a couple of the final results, which are like very, very heavily aggregated to the point where even if you wanted to make it differentially private at that point, the noise you would have to add wouldn't be all that large because the size of the data sets were so big. But the question is, how can we allow someone else to check if our results are correct, to rerun the analysis? So rerun the analysis on a different time range, or check, how do we actually provide that kind of transparency? I say we, I don't work at Twitter anymore, but still. And so one of this has led to Twitter partnering with Open Mind, which is a big charity. They're a really cool company by Andrew Trask, amongst other people. And what they are doing is they are doing differentially private query tools. They actually have open source libraries that you can use to make differentially private queries on various databases. So the idea is that Twitter is partnering with Open Mind, and they are using this political amplification study as an example. They want to create a database that you can query with DP, queries that have DP guarantees, so that people can reproduce our results in that way. And there was a question before about how to set epsilon. What's a reasonable epsilon? And it's kind of funny because nobody knows the answer to that. So even in these sorts of conversations, we were saying is like, oh, maybe we give people like an epsilon of 10 privacy budget. And then if they can answer if they can get the answer they want with epsilon equals 10, then we will increase it to epsilon equals 20, and maybe they will do it. So essentially it's kind of finger in the air type of arguments, and it's usually about what's the smallest epsilon that you can get away with while still providing the utility that you wanted to provide. Provide the strongest guarantees that you can without jeopardizing the utility of the analysis you're trying to do. I think that's the best sort of heuristic. So that's a practical example of DP. It has nothing to do with machine learning other than the fact that we studied the effect of machine learning algorithms. And so now I'm going to talk a little bit about machine learning models, and I'll draw the same figure that the authors of this paper that I will talk about, which is deep learning with differential privacy, all the way from 2016, drew in their presentation. So usually how you do machine learning is you have a data set, which looks like this, obviously, and then you have a learning algorithm which produces a model. And then you assume that if you're say a company providing services on the basis of this model, you can keep the data safe, so you don't have to worry about people actually getting access to the data, and you can also assume that you keep the model safe for the purposes of this. But then there is some sort of public API or whatever prediction service. So here comes a sort of input image. Let's say that this is an image, classify my picture, and it's going to output a prediction. And the problem is that even if the person doesn't, or let's not consider how somebody who wants to get some information about this database, whatever it may be, how they might go about attacking the system and getting that information. So obviously, one of the things that they can do is they can just design specific inputs to give to the system, so that by observing the predictions that the model made on those specific inputs, they can get information about the model. You can reverse engineer some things about what Google's model is by if you can query their service with enough kind of queries. So you can get some information about what the model is. And if the algorithm provides no guarantees that it doesn't leak information about the data set into the model parameters or the way the model works, then by induction, theoretically it's possible to for the attacker to obtain information about the data as well. And we are talking about like theoretical information theory, which is sort of, you can think about the mutual information between two quantities as the best thing somebody can do to try to predict one of the variables based on the other variables. So you don't, even with relatively simple assumptions about what an attacker can do, it is conceivable that you can do, you can reconstruct some of the training data from doing this. Okay, so I wanted to ask a lot of questions because that gives me a lot of time. I don't actually have to talk about the paper. Who can give me an example of a machine learning algorithm? Anything, doesn't have to be deep learning, that you think would do particularly badly on privacy in this sort of scenario that I outlined.
One nearest neighbor.
Nearest neighbor, okay, nearest neighbor, good one. Yeah, I mean, I'm not going to ask why because I think everybody will go, aha. Anything more commonly used or more commonly used 10 years ago, where everybody used deep learning?
Generative models.
Generative model, why do you think they would be?
So like, for example, they can reconstruct data from the original distribution, and that can be
Yeah. So one of the impactful things was that so a particular kind of generative model is text. So you can prompt a language model with something like my long card number is, and then ask the network to, or the method to complete this sentence, and the network might have memorized actual credit card numbers, and then it's going to just spit out credit card numbers. This actually happened in LSTMs. I don't know if anybody's demonstrated this in something like GPT-3.
I think in Codex, people have shown that if you just type like sort of doc string for something that is similar to what
It's actually going to retrieve the.
Yeah, so like it will write code from other users which they have written, which are working in very similar areas, and people have exactly found correspondences in that regard.
Okay, so so these models can, at least in theory, memorize data points, and then there's way to get them out. Yes. Okay, anything else? I actually had another example in mind.
Kernel regression.
Kernel regression? Yeah. Is it kernel? Did you say kernel?
Yeah. Yeah.
Yeah, I haven't heard that word in 5 years. Yeah, so so if you think about support vector machines, for example, or support vector regression, the support vectors are actual data points. And so, the parameters of the model are data points. So if you have access to the parameters of the model, you have access to data points. And it's also possible to, by querying an SVM, you can probably reconstruct what the support vectors are. You just, you can do that. But yes, so it's not just deep learning that's going to have this problem, that it's going to, deep learning is bad because it memorizes data points and we're Bayesian and don't like it. All kinds of machine learning models have this sort of problem, and we have to think about how to fix that problem. And so in practice, there are a ton of different types of attacks on model privacy. Here is a very interestingly titled GitHub repo, awesome ML privacy attacks. I think awesome refers not to the attacks themselves, but the repository. So you can see a ton of different papers which detail different kinds of attacks you can do. One of the most common one is membership inference attacks. Does anyone know what membership inference attacks are, or can guess based on the name?
To infer the membership to a particular group of each individual.
Almost. Yeah, this is about the membership in the data set. So this is whether you can guess if a particular data point was or was not in the training set. And this is the closest related to the actual DP definition, because if you think about this lambda that we had before, if you think about this lambda of, was it P prime or XX prime? I don't know what your notation was actually. This was log of P prime of the response given P of response. And so if you had access to this P and P hat, so your base optimal attacker, then if you plug this into a logistic sigmoid, then you basically have a classifier for membership inference. This is the base optimal classifier to determine whether you are in P or in P prime, and P prime only differ in whether a particular data point is in the data set or not. So you can think of differential privacy as bounding the success probability or bounding the predictive probability in a membership based attack, like whether a particular data point is in or not in the data set. And another type of attacks are reconstruction attacks. I already showed you the example with the credit card number, but you can reconstruct images also from models. And this is a very strong attack that is possible because we are in a federated learning attack. So here, federated learning is when the data is on users' devices and they don't send the data to, say, Google. They calculate a gradient on their device, on a mini batch of data that's on their device, and then they send the gradients to the central server. And if you try to reconstruct the data from those gradients, it's actually possible to verify high accuracy. So this is the method that sees the gradient update of a model, and it reconstructs the image that created that gradient update. And you can see, reconstruct faces with pretty high accuracy using this technique. This is called the deep leakage from gradients. And you can do this not just with gradients, you can also do other things from that don't have access to gradients. Okay, so yeah, machine learning models can have problems in this way. Deep learning models obviously can have problems like this. So how can you design an algorithm that's going to guarantee differential privacy and then circumvent these attacks? And this was the first paper that kind of practically did this. There were a couple of papers that tried to do this before, but this is the first kind of working version of a differentially private learning mechanism for deep learning. So the function f that we talked about before is now going to be the entire learning algorithm that maps from the data set to, say, the parameters of the neural network. That's the function that we want to replace with a random function that calculates a random set of weights. And luckily, stochastic gradient descent already is a random function. It's non-deterministic in the way it works. So I'm going to first show you what that algorithm looks like. And it's not very surprising. So the input is what's usually the input, except that now you have this C and L, which are extra hyperparameters. So we compute the gradient. Notice we compute the gradient on each individual data point here, GI. So as opposed to normal like gradient descent, where we calculate the average gradient on the mini batch, we now calculate the gradient data point by data point. This can be done efficiently, but we don't usually do it because we don't need it. Then we click the gradient. Who can tell me why we click the gradient? What's the purpose of clicking the gradient? Based on the verse. No, you can do that.
I don't remember what they call the delta.
Yeah, and this is to basically explicitly bound the sensitivity of the function. So the sensitivity was what's the biggest change that leaving out a data point can have on the function. So here, if the gradients are very huge for one data point, then the function can change a lot, or the function in terms of the parameters function of data points can change a lot. So we are explicitly bounding the L to norm by C. for the square delta node to the outer node C. And then we just apply a relatively standard, add Gaussian noise, which is one of the simple version of the Gaussian mechanisms that we saw before. And again, here, the same constant C appears because you have to use the sensitivity of the function to figure out how much noise you want to add. But this one constant kind of, as you are making C bigger, you allow bigger and bigger gradients. So the gradient clipping is less harsh. At the same time, you're adding more noise. So either ways, you lose some of the information in your gradients. Either you clip them very small, and then you add a little bit of noise, or you allow them to be large, but then you add a bunch of noise. So that's really the algorithm. And I think the basic algorithm here hasn't really changed that much over the years. The main, this is 2016, the main kind of new things about this was making this C change dynamically. One of the things here is that maybe early on in the training, the magnitude of the gradients might be large, and then later on it's going to be small, or the other way around. Who knows these days? And then you might want to change C in reaction to how big your gradients are. So you can have adaptive versions of that, and so you kind of control that C hyperparameter as you go along, and these kinds of things. But other than that, this is the basic mechanism. It's very, very similar to normal stochastic gradient descent. And then one of the other things that they do is, although they don't do it in this paper, you can make the clipping constant different within the network. So you can clip, for example, different layers to different, if you have different magnitude gradients or something like that. So you can do a bunch of things with it. Same way as you can change SGD in a lot of different ways. The one thing that they emphasize in this paper is that they talk about lots as opposed to mini batches. So they have an additional hyperparameter, which is how big the size of the data is that they calculate the average gradient on. And this is the hyperparameter L, and it doesn't have to correspond to the batch size. This can be larger than the batch size. And in fact, in their paper, they calculate these gradients and clip the gradients of multiple batches before taking a gradient update. And so this allows you to, again, trade off, like better control the trade-off between accuracy, which might be hurt due to the noisiness of the gradients, and the privacy budget that you have.
Sorry, this is, so if we fix L to be equal to the batch size and set C in a sensible way, like would this be then related to stochastic gradient launcher dynamics?
Yeah, I think SGLE does something like this, except for the gradient clipping. And then you can reason about it. Yeah, I mean, stochastic gradient launching dynamics is just add a little bit of noise to the gradient.
Yeah, I was just wondering if there's like anything like deeper to this about it that you might know. Besides that they look very similar.
Yeah. Okay. I don't know. Maybe there is. I don't know. There is going to be something about generalization if I get to those points, which is a little bit deeper. And then there is related generalization work on SGLE that there might be a connection there. So in fact, the main innovation is not in the training algorithm itself, but in what they call privacy accounting, which is how do you know what your epsilon and delta is for this particular algorithm. And you can do it in multiple different ways. The naive way of doing it is using this thing, which is, I already showed you the strong composition theorem. The strong composition theorem is that if you have functions that feed into one another, so there is one mechanism and the output of that, which is random, is fed into another second query, which then returns another random answer, you can bound the differential privacy of that entire chain of operations using the composition theorem. But that composition theorem, it treats each mechanism as a black box. So it knows what the epsilon and delta are for those building blocks, but it doesn't really know what's going on inside them. there is any kind of correlation between between the two mechanisms, or if there is anything specific about the noise, it doesn't know that. It gives a very loose bound on what the epsilon and delta are for the entire composition. And so if you start, and I'm gonna fast forward to this because it's easy to see. If you try to run this DPSGD algorithm, so you keep cycling through data, and you estimate the epsilon, every step consumes a certain amount of privacy budget, and this epsilon is sometimes called the privacy budget. It obviously goes up the epsilon in your bound, because the more steps you take, the less privacy is guaranteed. And it goes up almost linearly. And so if you take 350 epochs on whichever data set this was, I will only store CFAR, then you quickly get up to an epsilon of 20, which is high. So one of the ways you can innovate here is by realizing that the actual epsilon for this algorithm isn't really 20. This is just an upper bound. So when you use the strong composition theorem, you do a bunch of upper bounding inside. And so if you do your maths a little bit, if you do a little bit more math and you know a little bit more about what exactly your algorithm is doing, then you can construct better bounds. And this particular bound that they came up with does this. It's exactly the same algorithm. It's just that you're now calculating what your epsilon is using a better bound, which means that now, you can go all the way to 350 epochs and actually know that you've only used up 4.5 epsilon. So this allows you to basically, for example, keep running this algorithm for longer if you have a fixed privacy budget to begin with, like I'm not going to go above 10. If you use this privacy accountant, which is the composition theorem, you would stop here, and then accuracy is whatever accuracy you reached up until this point. But if you have a better accountant, then you can keep going for longer. And so that's the main innovation of this paper is this called so-called moment accountant. And I'm gonna roughly say what the insight here is, but I think this may not be the most up-to-date version. Here, this equation 1 is their notation for what we use lambda for. So this is the privacy cost. It's just, I think I like this notation because even though it's very verbose, everything is very clearly spelled out. So the mechanism M is a gradient step. The OAKS is any other inputs, like the previous parameter value, for example, would be an auxiliary input. D is the data set, which would be a mini batch or a lot in this case. And then O is the output of the mechanism. And so you have the probability that the mechanism outputs O if its input is D, divided by the probability that it outputs the same thing if its output was a JSON data set. So that's the same thing there. And what we are going to do here is we are going to keep track of the moment generating function, which again is not very intuitive, of this random variable. So this is a random variable because O is a random variable. So this log this versus that is also a random variable, and it has a moment generating function, which looks like this in this notation. Equation 2, this is alpha M. And what's interesting is that in differential privacy, two things are going to happen, which makes this moment generating function interesting. The first thing is composability, which means that if you compose multiple mechanisms together, feeding the output of the previous mechanism to the next mechanism, like in SGD, feeding the output of one step to the SD equals the next step, then the moment generating function for the privacy loss of this composed mechanism is upper bounded by simply the sum of the moment generating functions for the individual steps. So this makes this accounting very easy because you just calculate the moment generating function of the privacy cost of one of your current SGD updates, and you just keep summing that up over the updates that you're taking. So this is why they use the moment generating function. And the second thing is the moment generating function comes up in a lot of tail bounds, for example, Markov inequality and things like that. So the moment generating function can be used to bound the probability that of very extremely high or very extremely low values of a random variable. And this is precisely what you want to bound in differential privacy. You want to say that the probability that this privacy cost is higher than a certain value, epsilon, is less than delta. And that's, you know, if you have the moment generating function, you can plug that into Markov's inequality and directly get a DP bound at the end. So that's their moments accountant. And this is what allows them to do this, this thing here, which is run the same algorithm, but then provide stronger privacy guarantees at the end. So that's the DPSGD, and you know, they report results on this was MNIST and CFAR, which, you know, on MNIST you can get with a reasonable privacy budget in single digits, which is what they call reasonable. You can get almost as good as not doing DP. On CFAR you get a 10% point drop or something like that. So it wasn't as good. But previously, the epsilon that they could use, the best epsilon that they could use was like in the thousands. And for like something that they did anything with these data sets, and they could bring that down to single digit epsilons for like reasonable models. One important point that is a caveat for these achievements, where is that? I don't know where they have that differential private PCA. So they talk about using either PCA first on the data. This is back in 2016. So you know that's kind of nobody would do that these days. So they did differentially private PCA on the data first, because then it made the subsequent learning problem that much easier for them. They couldn't train this completely end-to-end with the whole network with DPSGD. The other thing that they did is, which I think is a very smart idea, is that they transferred pre-trained convolutional layers from other data sets, and then only trained or fine-tuned, only use DPSGD for the fine-tuning, which I think is a smart idea because you don't care about leaking information about, say, ImageNet. So taking ImageNet pre-trained networks and fine-tuning it on your private image data set is probably a very smart idea to actually practically approach differential privacy, because then you don't have to worry about training the whole model end-to-end entirely with differential privacy guarantees. Right. And so, yeah, I think that's what I wanted to say about this method. There are implementations of this online that you can probably just plug into your machine learning, deep learning training, probably as a replacement of SGD, I assume. I haven't tried that myself, but I don't think it can be that hard. And yeah, and are there any questions on the DPSGD stuff?
Yeah, I have a question. So if I understand correctly, maybe I don't, but like as I understood the guarantees or the formulas in here, they're about like adding or not adding a single data point. So if I have if in this like private data set there's like 10 pictures of me, is it like still possible to reconstruct them, or like the like guarantees don't say anything about that?
So there is a concept called group differential privacy. Is that as well? So group differential privacy is when you want to be differentially private with respect to removing an entire group of data points. Exactly like that. So what changes in the definitions is that what you consider neighboring data sets will change. Like now neighboring data sets include not just one data point being in there or not, but like an entire subset of the data being there or not being there. In terms of whether anybody has done that sort of thing for SGD. And how that would work in practice, I don't know precisely, but yeah, I'm assuming people are thinking about it.
Do you think this direction is related to the memorization literature that people are trying to focus on? In that case, like the focus is just to ensure that the model doesn't overfit to particular examples and just directly memorize. But do you think there are any parallels between them and similarities between these two directions?
Yes, and then I was just gonna go in that direction, which is what's the connection between DP and generalization, and of course, memorization is then also potentially related to generalization. So yes, there is a lot of different literature that connects differential privacy to other properties of machine learning methods, including generalization. And I think one of the mechanisms by which differential privacy would enable models to generalize better is by preventing memorization. It wouldn't like prevent memorization all the way, because there is a delta and with a small probability it may still happen. But yes, I think my assumption would be if you train your neural network with differential privacy, it wouldn't be able to memorize data sets. So for example, those the 2016 paper that shows the rethinking generalization paper, if those of you know it, where they showed that a neural network can fit completely random labels, fixed but random labels on CFAR. I assume that if you try to do it with DPSGD, you wouldn't get very far.
Exactly.
Or your epsilon would blow. And I wouldn't be surprised if many people have done that sort of experiment. But I'm also not aware of anyone using DPSGD specifically with the view of improving generalization or preventing memorization. I don't think that's commonly done. People usually think of DP as something you do if you work in a privacy sensitive application, not because you want to improve your model performance. Because even though your generalization might be better, the training loss that you can achieve will be higher. So the difference between training and test will be small, but your training loss is so poor that it doesn't help you that much at the end. So one other thing I wanted to briefly mention is we already discussed a little bit about connections to information theory. So if you take this random variable, the log p of I think it was r and p prime of r, and you take the expectation of this, where r is sampled from the same thing, then of course this is the KL divergence. KL divergence between p and p prime, if r is sampled from p. And so, in information theory, we would be, if we came up with differential privacy, starting from the starting point that we want the model to behave similarly for two data sets that are adjacent, maybe we would have come up with, we need to bound this KL divergence, that we want the outputs to have a similar distribution in these two scenarios. And I think that would be perfectly valid. And we looked at this zero-centered DP, which can essentially interpolate between the KL divergence and the very strict DP, kind of worst-case scenarios. But similar things actually show up in the generalization literature. And one of the sort of connections that I wanted to make here is the connection to conditional mutual information bounds, which are on generalization. So now we are completely outside of the privacy space. We don't care about people's private data anymore. We care about, here's a machine learning model that's trained with a random algorithm like SGD. Can I say something about how well it will generalize or not? And so one of these this approach is bounds generalization by using a mutual information in the following way. So you have two data sets in that sense, D1 and D2, which are not adjacent. They are assumed to be IID sampled from the same underlying distribution. So let's say that D1 is the training set and D2 is the test set. Training test set. So like two identically distributed data sets. And I toss a coin, and then a coin toss Y. And so it's sort of, I'm going to explain this as a two-player game. So we both see, so I see a coin toss. I see coin toss. I see Y, and we both see D1 and D2. But then, based on my coin toss, I'm going to take my algorithm and train it on either D1 or D2, and I'm not going to tell you which one. So I'm going to take theta equals, I take my algorithm, which is SGD, whatever training algorithm I have, and I apply it to dy. Y can be either 1 or 2, and I use the data set that I train on. And I give you the theta, and I ask you, can you tell which one of these two data sets did I train my algorithm on? Which one did I use as a training set? And so, and the question is, how well can you guess that coin flip? So what we are going to measure is the mutual information between theta, the output of the algorithm, and Y, the coin flip that I see but you don't have access to, given D1 and D2, given the two data sets that we both have access to. So this is the CMI. And this is a property of the algorithm and a property of the data generating distribution. And this conditional mutual information shows up in generalization bounds. This is relatively recent work from 2020. So you can say, I don't know if it shows up in the square root or not, but something like training loss test loss minus training loss is upper bounded by some function of the mutual of the CMI. So basically, why would this be the case? So imagine that this mutual information is high. It means that my algorithm returns completely different distribution of potential outcomes depending on what data set I train it on. This means that my algorithm is very, very sensitive to the specific choice of data set. So probably it's going to do different things on the test set than it's doing on the training sets. So I can't trust my algorithm to be doing the same thing on a training and test sets. And that's not good. On the other hand, if this conditional mutual information was, say, 0, it would mean that the algorithm returns the same answer irrespective of which data set I trained it on. So for example, this conditional mutual information might be 0 if your algorithm just randomly initializes a neural network and doesn't do any training. It doesn't tell you anything about which data set I did not train my network on. And indeed, for that method, the test loss and the training loss in expectation would be the same. I think this is, by the way, an expectation over training data sets. So this is sort of the intuitive connection between this conditional mutual information and generalization. There are like more formal bounds that you can look up. This is an active area of research. And so I wanted to mention this because this is very similar to the differential privacy in some sense, except that in differential privacy, we care about these D1 and D2 being adjacent data sets. And instead, if you think about data sets that are randomly resampled data sets, then you get into this territory and this formalism. And if you think about adjacent data sets, then you get into the DP type of privacy arguments. But in my mind, the two are like very strongly connected. It's just looking at the problem slightly differently. And so this kind of explains why differential privacy might actually be a very useful property for generalization as well, partly by preventing memorization. So that's the range of things I wanted to cover. Does anyone have any questions to either of us? Not half an hour later, half an hour.
Yeah, fine.
Has anyone here used DP or heard of DP before? Does research in DP? Yeah, in what context?
Yeah, I've done some research in DP. Voice from above.
Actually come from the owl, it's great, mildly terrifying.
The owl has spoken. Yeah, did we say anything flagrantly wrong about DP?
No, it was all good.
That's a low bar. It's the worst case balance. Right. Thank you, everyone. Thank you.